Oh, so hi everyone. I am Chen, and today I'm going to talk about the mechanism to generate free floating planet from the killed circumbinary planets. And this was created by different people in different institutes in the UK and the USA. So in previous talk, I believe Jeremy has persuaded you that planet formation can happen in the circumbinary disk. If not, I will content him later. So this, so we know that binary is very popular, and according to this simulation, uh, sorry, okay, according to the simulations, then as you can see that planet should be formed around the one of the star around the binary, and it could be formed around the binary. So it's P type and S type. And as Jeremy mentioned, that if the big friend of the star world, then Tatooine is a very classic P type planet or circumbinary planet. So unlike the planet orbiting around the single star, it's a two-body problem. So you can from I think from your intuition, you can say yeah. So because it's a three-body problem for the circumbinary planets, so it's more unstable. So it can be the mechanism to produce the free floating planets. So oh yes, so you may think that if the planet is very close to the binary, then it may get ejected from the system. So 25 years ago, the Holman and the Wilger, they had already found this equation to express the critical semi-major exit. So if the planet is inner than this orbit, inner than critical semi-major exit, it will be kicked out from the system, and it depends on binary eccentricity and binary mass spectrum. And in general, so if the binary is nearly circular, then the planet can be more close to the binary, and if it is very eccentric, then the planet should stay away from the binary. Oh, it stay away from the binary. Okay, so from the observation, you see that half of convergent circumbinary planets are very close to the innermost stability limit here. And let's see, yeah, so a second planet cross over the critical radius will be injected out from the system. But this is just for the coplanar. So in Jeremy's talk, we know that circumbinary disks can be very misaligned. So it can be misaligned. For example, like this IIS 43 is 16 degree. And the question is how we define the incarnations of the circumbinary disk or circumbinary planet. So let me explain the detail. For example, in this figure, so LP is the angular momentum vector of the binary, and LP angular momentum vector of the planet. So if it's parallel to each other, then it's a coplanar. And then uh, so if the planet is in the misaligned orbit, then the incarnation is the mutual incarnation between LP and LP. And if LP and LP they are perpendicular to each other, then it's the coplanar orbit. And finally, then if it's parallel but in the opposite direction, then it should be the retrograde orbit. So why this is so important is because there's the uh, very different orbital interaction or orbit dynamic for the misaligned planet. So let me show this sample. The first one is called the nodal precession. So if this planet is misaligned but is smaller than the critical inclinations, then the angular momentum vector of planet LP possess about the angular momentum vector of the binary. So here is the 3D diagram. If we project to the I-phase plot, then we can see it's 10 degree processing. And if you keep increase the inclination, then yeah, so it's still processed about LP. And if it's retrograde orbit, then it's the same. It's also the LP also possesses about the LP, but it's in counterclockwise direction. And the other dynamic is the nodal libration. So for the nodal libration, it is required that the planet inclination is larger than critical inclination. At this stage, the LP possessing about the binary eccentricity vector. So this is this purple circle here. So we can see. So if it's above the critical inclination, then it starts to possess about the binary eccentricity vector. And we can keep increase until it's reached the 19 degree. So there's no any precession happens because it's in the stable state. So from this plot, we know there's a three type of the orbits, and then there's another oscillation and another vibrations. And it's either says about the LB or binary eccentricity EB. And but actually, this vibration island can expand with increasing the binary eccentricity. So let's mean that around the very eccentric binary, then the planet can undergo another vibration. So this means that the planet can undergo given orbital interaction to the binary if this misaligned, unlike the coplanet. So here, so for the if we have the binary and a planet, now we need to consider we need to consider another oscillation with binary and a resonance with the binary. So in further simulation, I will show the result produced by the rebound, and thanks Reynolds provide very good code for us to use. And here is the result. So in this stability map, first we consider the mass fraction is 0.1. And you can see the innermost stable radius is actually a retrograde orbit. So which means for the sorry, I forgot to mention that the binary eccentricity is just 0.2, is a low eccentric binary. So this is the most stable orbit for the circumbinary planets. On the other hand, if we increase the binary eccentricity to 0.8, then now you can see the most stable orbit of the circumbinary planet actually is nearly the polars. Okay, and then if we change the mass fraction to an equal mass binary, then we still see that for the low mass binary, low eccentricity binary, then the most stable orbit is still retrograde. And then if we change the binary eccentricity to 0.8, then we see the same effect. So that's why the innermost stable orbit for the circumbinary planet in the low eccentric binary system is retrograde orbit, and for the high eccentric orbit, the most stable orbits are the polar planet in the polar vibration orbit. So right now, it's just the single star case. And we have to, it's inevitable to talk about the multiplicity in the circumbinary system. So which have the given multiple planetary system in the binary. And this is this table. I couldn't find the website, so this is actually the last year's result, and there should be more of the planetary system we will find, and we believe it's similar to the circumbinary system. Okay, so for the this cartoon shows that we have binary and we have the two planets. So we have to consider not only another oscillation with binary, resonance with the binary, and we also have consider the resonance between the two planets and the Q oscillation between the planets. So to introduce the Q oscillation between the binary, I think I need to solve the fourth order inverse matrix. But yeah, so there's not enough space on the whiteboard, so we just see the results. Okay, so now let's go back to the single star. Okay, so this is the star, just a star, and we have the two Jupiter mass planets. Okay, and this inner Jupiter is placed at the 10 AU from the star. And you can see this is a stability map if we have the two Jupiter mass planets. So the y-axis is the semi-major axis of the outer Jupiter planets. So you can see in most of my simulation, they are very stable unless they are very close to each other, say roughly about 13 AU. So that's why for the planets around the single star, there's two planets. They must be very close to each other to produce the planet scattering. Okay, and this is the result from the if we consider the binary system. So here we have the Jupiter at outer and the Earth mass planets in the inners, and we place the inner planet at 5 AB. So AB is separation of the binary here. Then in this picture, we consider it's a circular binary. Okay, and the y-axis is the mutual heel radius between the two planets, and there's a criteria. So if this delta, this mutual heel radius, is smaller than the two times square root 3, roughly about 3.4, then they should be unstable. So that's why we start our simulation around this value here and delta from this value, and we vary the inclination to the binary from the 0 to 180 degree. In this plot, you can see, so if the planet, this planet have the mutual heel radii above this value, then if it is coplanar or retrograde, they are quite stable. Okay, they are quite stable. However, if you just have very small misalignment to the binary orbit plane, then it's become unstable. Okay, so become unstable, and it can this region can expand to the 5, and the other unstable region is the 221 and 321 resonance regions. In this case, you can see most of the stable planets is the outer planet, so which means the massive planet can survive in this simulation. And on the right panel, you can see we consider the planets around the eccentric binary. So in this eccentric case, you can see the unstable orbit region expands, and then you have the more unstable orbits in the 221 and 321, and even inner than the 221 resonance. Next, if we switch the order of the planets, so now the inner planet is Jupiter, the outer planet is the Earth. So we see the same result and very similar maps to the previous upper panels, but at this case, we can see the survivor is still Jupiter. And we know that it's due to the planet-planet interaction. So we want to know what's the minimum mass to trigger this kind of the instability. So in this simulation, I consider the same, the binary, but we have the two equal mass planets. So one is Earth, so two of them are the Earth. So you can see there's stability map. Okay, so in general, we can say, yeah, this kind of system is quite stable. And then if we consider the bigger planets like super Earth, 10 times to the Earth mass planets, then for the circular binary, still very stable. And for the eccentric binary, well, we start to see many unstable orbitals inner than the 221 resonance regions. And then the next, if we consider the Neptune-sized planets, yeah, so it's still stable, but we still have some unstable orbits. And then in the eccentric binary, we see more unstable orbits. And finally, if we consider the Saturns, and then we see the very similar picture as before. Let me point out, this simulation actually is a scale fit. So I assume that the mass of the binary is one solar mass. But if it's smaller, then to trigger this kind of the instability, then we just require the smaller planet. So yeah, so this Jupiter, yeah, Saturns. So here, this is my summary. So there are very complicated orbital interaction between the circumbinary disk and the binary. So circumbinary, so it's planets and the binary, and it results the orbital instability, and it could provide the significant numbers of the free floating planets. And if the a single circumbinary planet may become the free floating planet, as if it's inner than the critical semi-major axis. And this depends, actually, it's not just depends on binary eccentricity or its mass fraction. It also depends on its incarnation because I have shown that there's a given orbital dynamics which interaction between with a given eccentric or circular binary. And if the binary contains host two or more planets, the resonance and Q selection between two planets plays a role. So even though their separation is really far, they can still be stable. And then the massive planet can survive. And this result indicates there should be more low mass free floating planets. And the demographic data of the circumbinary planet is crucial to understanding the contribution of the free floating from the binary system. So that's why I put the several satellites like Earth 2.0, JWST, and Roman and the TESS. So we hope we can find more misaligned circumbinary planets in the future to confirm whether this mechanism is correct or not. Thank you. Yeah.
So now, open for question. Oh yes.
Nice talk, Cheng. A quick question: does the initial orbital phase of the planets affect the stability? So my thinking is, you mentioned so you had two planets around a single star. Say one planet is 0 degrees, other planet's 90 degrees.
No. So they are they're coplanar. The planet in my simulation is coplanar.
Right, I'm saying, but does the initial orbital phase of the planet like affect the stability? If you start both the planets in the same orbital phase, like
yes,
pi.
Yeah, two over pi. Oh, sorry, pi over two.
Right, but if you kind of change the combination of the two orbital phases, initially does it affect the stability?
Yes. So if the phase angle is 0, then they just undergo another nodal precession and no nodal librations anymore. So I show the result in my three-body paper. So three-body problem paper. So it's in 2019 B. Yeah. So in this paper, we consider the longitude of the ascending node is 0. Yeah. Case. Yeah.
Any other question?
So am I correct that you were initializing your planets on circular orbits?
Yes, so all of them are in the circular orbit because I assume that if the planet is embedded inside the disk, the disk can dump the eccentricity of the planet, and so that's why initially we assume that the planet should be close to 0. Their eccentricity is very close to 0 unless until the disk pulse. Yeah.
Well, one might imagine that the binary force eccentricity in the disk and the planets forming eccentric disk and also inherit the eccentricity. So I was just curious if you experimented with seeing if you could get a little bit more stability out of, say, putting planets on sort of eccentric ellipses.
I think it will enhance the instability region. So yeah, so I guess that's my expectations about that.
So I have one more question.
Yeah, that too.
On this question, but if the options are aligned, or the patient, the longitudinal patient aligned with this forced eccentricity, so I don't think eccentricity can affect the stability. I mean, if the binary and the planet ops are aligned, so it's like a circular, intercircular case. Yeah, forced eccentricity.
Forced eccentricity. So you mean if the planet is eccentric, orbit is eccentric, they may not enhance the stability. Okay, yeah. So
That's my guess.
Okay, then I didn't run the simulation with eccentric planets, but yeah, I mean it's more. Yeah.
So question. Okay, so thank you very much.
Yeah, thank you.